Hello, everyone. Welcome back. So we're going to continue from yesterday. This is the third day of this series. But let's.
Thank you. Thanks everybody who is back. So as promised, we are starting a second mini chapter of this mini course. So mini chapter. This is going to be about algebraic constructions for extremal problems. So let me first introduce what I mean by extremal problem. I would expect many of you would be already familiar with this kind of things, but let's just start so we're all on the same page. So let's look at the what's called a Turing problem. So what's a Turing problem? We have some forbidden graph G. So G, so it's a F, it's a F forbidden graph. And we want to find some graphs G which don't contain a copy of F. So not containing a copy means it's a subgraph, not an induced subgraph, not as a minor, not a subdivision, as a subgraph. So G is F3 if it contains no subgraph isomorphic. So I will not tell everything about the problem. So I will only introduce notation. So the extremal number, Turing number, E of F is the maximum number of edges in any F3 n vertex graph. And the if the forbidden graph is not bipartite, then there is a very satisfactory answer, which is a theorem of Ordish and Stone, which basically says, okay, so this is a number. What is this number? Is somewhere between 0 and 1. It's strictly bigger than 0. It's bigger than a half, in fact. And the meaning of the number is that you should basically partition your vertex set into several equal parts, put all the edges in between, and if so the number of how many parts you should choose depends on F. It's basically just choose as many parts as you can, and this is basically given by this number, and this is up to lower order terms, the best possible construction. Okay, this is what we want to focus is a situation where this F is bipartite, in which case this number vanishes, and this is not actually any really good. So in this case, there is the result of Combinatorics, George, Turing, which says that once you forbid any bipartite graph, you no longer get a quadratic behavior, you get a subquadratic behavior. More precisely, the exponent becomes less than 2. So since way I will state it is as follows, I will write for KST to be the complete bipartite graph with parts S and T. So this is S, this is T. And the result is that if once I forbid that, the bound is T to the 1 over S n to the power 2 or S plus something like S. What's important that the exponent drops, it becomes 2 minus 1 over S. Why am I focusing on the complete bipartite graphs? Is because every bipartite graph is contained in some complete bipartite graph. So once you can find a copy of a complete bipartite graph, you can find a copy of any subgraph of it, and therefore this transfers immediately bound to any bipartite graph. Okay. Though it's not the focus of main topic, let me just quickly go through the proof. It's like will take us 2 minutes, and we'll basically see where the numbers come from because that's useful. So proof. We're going to do induction on N. If there exists a vortex whose degree is less than S, we can remove it and induct. Right? This terms becomes n minus 1. Okay, this is even bigger. So this is we can just induct. So without loss of generality, degree of every vortex is at least S. Then we are going to count the following configurations. So they consist of a center vortex and S neighbors. So let's say Z be the number of such graphs inside G. So number inside G. And we can count them in 2 ways. On one hand, we can pick a central vortex and choose the neighbors then. So we are choosing the central vortex first, and then we can pick the neighbors in degree of this vortex, choose S neighbors. Now, because degree of every vortex is at least S, and the binomial coefficient function x choose S is convex when X is at least S. Okay, this is basically why I ensure this. I can use the Jensen's inequality to argue that this is smallest when all these numbers are equal. So we get the lower bound of 1 over degree of V. I choose S. N. Okay. Which is at least okay, I'm going to bound by normal coefficient. So first of all, this is first equal to the sum of the degrees is just number of edges times 2, which is at least n to the e n minus s to the power s over s factorial, because this is just product of this number, this product minus 1, this product minus 2, and so forth. And there are s factors. Each of them is bigger than this, and then we need to measure we have s. Now, as to the upper bound on z, we can think of course choosing the neighbors. There are and choose s ways of doing that. And once you chose them, well, since we are assuming that there is no copy of KST, if this S neighbors have no more than, this S verses have no more than T minus 1 common neighbors. So this is T minus 1, which is, okay, I'm just bound T minus 1 by T because I want formulas to be pretty. This is our bound by N to the S as x factorial, again, bunch of n times n minus 1 times n minus 2, etc. is at most n to this, and s factorial in the bottom. Put this together, what I'm left is, okay, s factorials, s factorials cancel. I move n around, take s root, so okay, I'm going to get the number of edges is going to be at most a half plus times t to the power 1 over s and to the 1 over s plus a half s. So in this case, we get even slightly stronger bound than promised, but it's okay. So this is a coverage of to run, and again, and good mnemonic to remember what this theorem is about. It's about coverage of to run graphs. All right. A natural question is, when given any result, is it sharp? Okay, so, is there a question about mnemonic? No? Okay. Okay, if there is, please let me know. Okay. So question is it sharp? And well, let me tell you what we know and show you some constructions and also tell you what we don't know. So let's start with the simplest case. K2 free graph. So for K2 free graphs, this is sharp. Okay, I mean when I say sharp in this section of the course, I will mean exponents are sharp. I mean, okay, there's something known about the constants too. I mean, which is basically these things. Again, in this particular case, we actually know this constant is sharp, this constant. But for now, basically, I will basically talk more about it. So let me just show you a construction just to get us in the mood for a bit of algebra. So structure. So I will make a bipartite graph. So the left part will be the plane over a finite field, so fq squared. So these are points in a plane. And by plane, I mean plane over finite fields. On the right side, this will be the lines in f q squared. So in other words, these are sets of the form x y y equals ax plus b. Okay, and again, I'm writing here non-vertical lines. It's not going to make it much difference, but you can add vertical lines in one topic. So okay, so we have a bunch of lines, and I'm now defining a graph. So the point here is connected to a line here if it lies on that line. This is my graph. Just a containment graph, or as it's commonly called, incidence graph. Now, first, let's check that this does not contain K22. Well, K22 is the only way I can have a K22 since graph is bipartite is have two vertices on the left and two vertices on the right, because if I have more than two vertices on one side, then there ought to be an edge between them, but it's bipartite, there are no edges inside the parts. Okay, so say have two say points. Well, if I have 2 points, P and P prime, well, which lines is contained? Well, there's only one line is contained on, right? And this is the usual geometry. So not 2, therefore I'm no K22. But that's an easy proof. And okay, when I say okay, lines, points, okay, I'm going to use the usual linear algebra to argue this, but again, if you want to do formally, but intuitively, we're all familiar with point properties of points. Okay, and what about the size of the graph? Well, the number of vertices, well, it's going to be the q squared vertices on the left. And again, since I did not use vertical lines, there are also q squared vertices on the right. There are 2q squared vertices on the north. And what's the number of edges? Well, for each vertex on the right, each line, like you square them, there are q edges because each line contains q points. So we get q cubed. And this is 2q cubed, right, to the power 3. So it's exponent is 3/2 is okay. This construction can be improved in various ways. So let me maybe just say a couple of words how. So first, you can get tiny bit more edges by adding vertical lines, obvious. But you can also do a bit more. You can pass from the affine plane to a projective plane. So remember I mentioned briefly the adding points infinity, and you get a little bit more edges that way. And the main improvement you can do is merging the left half and the right half by using duality. So right now here we have pairs. These points are given by pairs of coordinates x and y, and here we have points given pairs A and B. Turns out you can just basically merge it so together. So what you're going to get, something like this: A, B adjacent to A prime, B prime. If A prime, B prime is, that's basically it. And you can check this is going to give you a still H2 graph. Just this part, check this part, and that's it. Okay, and this is. Turns out, if you do the math, this construction will match this thing. Okay, let's move on. What about the K2T? Well, this is works because we can just use this. If you only care about exponent, we can just use the same construction. Because the exponent is still 3/2, right? We're still and we can still use construction. We don't contain K2, we don't contain K2x. Okay, so the next really interesting case would be K3 graph. So let me tell you construction for that. It's similar to this construction here. So except working in the plane, I'm working in a free space. So on the left, I have points in over FQ, in a free space over FQ. On the right, I have unit spheres. So, okay, so what's a unit sphere? This is exactly what you think it ought to mean. This is the set of all triples. So which satisfy the equation of a unit sphere. So the triple A, B, and C is the center of the sphere. And well, we can rewrite our usual equation. Okay, now it takes a little bit more thinking to see why this does not contain a K3. So, okay, so let's again pick 3 points on the right. And we want to check what's the common neighborhood. So in other words, we're picking 3 spheres. Okay, and neighborhood is, well, points lying on those spheres. And we also, so common neighborhood is just intersection of 3 spheres. Okay, so at this point, I need to put chalk away, because I will need to use my hands for the proof. Pen, baby. So we have 2 unit spheres in free space, right? they're going to intersect along a circle. Okay, we imagining basically like an Euclidean space. Okay. Then we're intersecting along a circle now, and the circle is once you know the circle, you actually know what the two spheres are because it's a unit spheres, right? It's not arbitrary large spheres that you can stretch. Now, if you add now a third sphere, you're intersecting this circle. Well, it's going to intersect in 2 points. Proof is complete. Okay. Now, of course, this proof is a bit of a hand waving. But how, if we're actually take this proof and I should try to turn it into actually a rigorous mathematical proof, what would we do? Well, we do the obvious thing. We were going to just write equations for those spheres, just to crank our algebra, right? And this is how we would write a proof, like, well, maybe do some kind of simplifications, like without the generality, one of them is at the origin, and so forth. Okay, this is how you write a proof, and it works. Now, and turns out that since FQ is a field, in that proof, you basically only use the field axiom. You're not actually using anything really else. That proof will carry over, except one thing. At the end of the proof, which I will not write because again, it's not an interesting exercise. At the end of the proof, what you're going to be using is that -1 is not a square in F. So that's a condition you will. So big deal. You're just going to choose your Q so that -1 is not a square. But for example, you can take it to be prime, which is going to 3 mod. Okay, and parameters are good. Let's just check parameters. The number of vertices is 2 times Q cubed, plus Q to the cubed versus on the left, Q cubed versus on the right. And again, number of edges, again, for each sphere, the Q cubed spheres. Okay, there are going to be, there are going to be basically Q cubed points on it. Because again, this requires something checking, but there's one equation, 3 unknowns. With some work, you can show there's going to be basically Q cubed solutions. Okay. So again, its exponent is going to be 5/3, and this is partial. Okay. At this point, we all get optimistic, like we can now solve all of them, right? We just need, for the next case up, we need to go to 4 dimensions and write something, some equation, and we should be done, right? Unfortunately, hasn't worked for anybody yet. It doesn't, I mean, nobody has proven that it cannot work. Maybe there is something, but nobody has managed. So the status is as follows. It's KS is open for S is 4, in particular for 4. What is known, and I will show you something. There exist constructions, and we'll see them. Of KST free graphs with the right exponent. So with n to the power 1 minus 1 over S edges, if T is much larger than S. So if T is much larger than S. And of course, the larger the T is, the easier it is, because if you don't contain KST, then of course you don't contain KST prime for any T prime bigger than T. So this is a bigger result. All right. It's a question. Sorry, you just make a sound. Remember, I asked you make sounds. Okay.
So for K-free graphs, can you use another quadratic surface to have the same information?
Yes. It's not. There's nothing terribly special about spheres. No. And in fact, again, for example, you don't even need the -1 to be not a square, because what you really want basically if you take this negative of this number to be not a square. So for example, it just pick this right number appropriately. So yes, there's quite a bit of flexibility. Yes.
I guess like K22, I think a random bipartite graph with some P being like onward with them, and that's gonna work as well.
Random bipartite graph is not going to work. No. So if you take a random construction, let me just maybe quickly say it. So I take random bipartite edge density P. What are you going to get? Well, the number of copies of, say, K22 is, well, if I fix 4 vortices, so there are n choose 4 choices, probability it's going to be K22 is P to the 4th, okay? And the number of edges is well, by Chernoff is P2 times n squared. So if you wanted to say deletion, you want to delete one edge of each copy from to kill them off. So basically you will want E squared minus n to the 4th P to the 4th. So this is edges remaining after you delete one edge from each copy. Okay, so you will want basically these two things to be the same, roughly the same. So you will need to be P should be P cubed should be n squared, so n to the negative 2/3, and so you're going to get result that this one, the extremal number is at least some constant, which I'm just too lazy right now to compute, plus 1/3 rather than that. Yeah, and basically this is not kind of unique to complete bipartite graphs. Basically, probabilistic arguments, they never, I mean, give you sharp results. Yeah. And so far, basically, the only times when we actually know what the sharp answers are, they are of this flavor. And I'll try to maybe say I will say more what I mean by this flavor once we have a bit more vocabulary. All right. Good. Sounds good. So, yes. So the constructions do exist if parameter t is much larger than s. And the part of the difficulty of making constructions for, let's say no, s is equal to t, is that we do know that there are no such constructions over real numbers. So what I mean by this, remember here I wave my hands, like imagine unit spheres in free space and so forth. And again, so the point is that if you look at these equations, which we wrote down, then they were really working over real space. And then again, we do some algebra and we can carry this over a finite field. And it turns out that there is, again, certain precise sense, which I don't want to delve into, there is, if you actually working over real numbers, you cannot actually make this construction, for example, for K for 4 free graphs. There is no 4-dimensional, you can take 2 copies of real 4-dimensional space, write a single equation. It's not going to happen. You're going to find K for 4s, no matter what equation you're going to write. Okay, so if there's a construction, it has to be somehow very finite specific. Okay, and we don't know how to make those constructions. All right. So plan is to show a construction for such a thing. All right. Right. We will go. So since we're going to be writing polynomial equations, right? What we plan, where we're going to construct it, we're going to write some polynomial equation. Well, except we don't know how to write it. We don't have any good idea how to come up with a good polynomial equation, as I told you. So we do what we always do in combinatorics. If you have no idea how to solve a problem, we just like close our eyes, poke things at random, and hopefully this is actually going to succeed. It's called probabilistic method. So what we're going to do, we are going to make our equation at random. But since we're going to be talking about polynomial equations, we need a little bit of language discuss their solutions, set of solutions. So we all familiar with sets of solutions of linear equations. These are called vector subspaces. So and the subject studying them is linear algebra. And then analogously, the set of solutions to a polynomial equations has a name. It's called a variety. So let me just basically introduce a little bit of terminology. I will say some of the results about them without proof, but again, will be, I'll give you some intuition. Okay, so we are going to be working over FQ. We're interested in counting, so equations over FQ. But it turns out, since we are working polynomial equations, we want to be able to solve them no matter what. It's very helpful to work over what's called algebraic closure. Okay, in this case, algebraic of FQ. Okay, so in the case, so this is okay. Formally speaking, usually if you take an algebra, it will be defined as a smallest field containing FQ, which contains the roots of all polynomial equations of Q. Okay, a more concrete way, maybe if you prefer, that FQ bar is just a union of all extensions. Okay, it's the Q to the C. So over T. So remember, the finite fields then nested. So if I like find finite field with a number of elements is the square of Q, it contains a Q and so forth. And they say so. And one finite field contains another one, is the exponent of one divides this one to the other. So you can just take a union of them all, because for any two such fields, there is a third one containing them both. And so it's easy to take a union. And concretely speaking, this is a field which is big enough. Okay. Okay, so that's now, so a variety is a set of solutions of a system of polynomial equations. So on, it's so this say A B F bar S zero for sample polynomials. Okay. Speaking of where the this is in the one x. Okay, so we have for example some polynomials in S variables, any number you like, and we look at a common set of solutions. That and that's what we call variety. So this is again, it's analogous to linear subspace. Okay, if the polynomial is linear, this will be linear subspace. Okay. Much like for linear subspaces, there is a notion of a dimension. Okay, so again, the intuition should be fairly geometric. Again, let me just draw a picture. So say if I take say equation like this is a circle. We want to say it's one dimension, right? If I take say a point, say this equation, so the intersection of two lines, that's a point. It should be a zero dimensional and so on. There are some minor annoyances. For example, if you look at the equation x squared equals 1, okay, the set of solutions is 2 points. I mean, it's still zero dimensional, but it has a kind of two parts. So to speak about it we talk about parts. So this is what's called irreducible variety. So definition. Variety is a variety is W is irreducible if it is not a union of two proper subvarieties. So for example, in these examples, the last example, the variety is not irreducible. It is reducible because it's a union of 2 points, and and point is a variety because, you know, for example, this point, it has an equation x plus 1 equals 0. This one has x minus 1 equals 0. If it takes a union of those two varieties, you get this. Okay. Good. On the other hand, say these other two examples, they are irreducible. Well, this is clear because we clearly cannot write point as a union of two smaller things. This one is harder, and we're not going to prove it again. We're not going to, you know, like algebraic geometry background. We are just going to state things and try to convince intuition why things work. We're not going to give proofs. So, but it is irreducible. It is not. You cannot actually, for example, write an equation defining, say, half a circle. Okay. So these are irreducible, and the quickest way to define a dimension of a variety is Y irreducibility. That's how we'll do it. Because, definition. Variety W dimension of W is the largest number D such that there exists a sequence of irreducible varieties that are properly contained in one. Like that. Okay, so an empty set. There is W0, W1. D, and this is okay. So this is definition. So in other words, there's a sequence. So the way you should think about the following: this each next one is a dimension of 1 higher than the previous one. So, for example, the reason that circle, according to this definition, is 1-dimensional, because the only subvarieties you can find, okay, again, I can all prove, in it are basically inside are unions of points. So, for example, you can find a subvariety which is maybe say these 2 points, but the only reducible ones are just a single point. So, the longest chain you can find is starting with a circle. Start the circle, go to the point, and go to the empty set. Okay, and this is the longest you can do, and therefore, dimension is a 1. For example, if you look at maybe an example, say, variety, say z equals to x squared plus y squared in free space. So in the variables like this. So this is equation of some kind of paraboloid in free space. So something looking like this. Then inside you can, for example, find various subvarieties. But we can find the circles here. Inside they can find a point, and then again empty set. So this is one longer chain of reducible subvarieties. Dimension is 1. Okay, this is a quick way to define dimension. But again, and since we're not actually going to use this for proofs like in one place, this is good enough for us.
Does it really match with our intuition with the user?
It does capture our distribution dimension fairly well. So if instead of working with the finite fields, I would work with the real numbers, okay, algebraic closure complex numbers. Then if you take a variety, then okay, locally solution set would be a manifold, and so which would be local, which is whose dimension is like so complex manifolds, which is chunk of C to D, where D is a dimension. Okay? For most points, so that's intersection points and such. You can definitely have a set intersection. Yeah. There are other different ways to define dimension, but again, this is not a algebra geometry course. Okay. This is a blank. We'll be using most as a blank box. Okay. You can define dimension. We define this. Okay, and I think let me see if I want to make one more definition before break for lunch. Because I think yes, I want to make another definition. I want to state as another bit of our toolbox, and this is probably the biggest ask for you to believe it. I will state a theorem. So a very useful theorem. Actually, so this is going to be Bukh's theorem. I mean, well, in the form I've stated, it's not definitely another form because we proved it. But okay, this is a version of what we call this. So let's say F S be polynomials. So we're working over this field. Let's be this field, but it works over every field. In S variables, and we are going to look at the variety which they define. So I'm going to look at the common zero set of these polynomials. If you want to think of pictures, think about S equals 2. This is a really good way to think about it. I have a plane and I have two equations, and I'm looking at a common set of solutions of two equations. So I'm intersecting two curves. So each equation defines me some kind of curve, and I'm intersecting two curves. And they're saying that if it happens that the dimension of this set is 0, because it might happen that when I intersect two curves, I'm going to get a curve. Like maybe they're the same curve. Maybe this is the same equations, right? It can definitely happen. But if it happens that the dimension is 0, then it's a finite set of points of cardinality at most the product of the degrees of this polynomial. Okay, and let me, again, since I'm not going to give proofs, especially proof of Bukh, that's definitely going to be towards the end of introductory course in algebraic geometry. Let me tell you the intuition, why you should believe this. And the reason you should believe this is because of if you look at this special case, say F1 is x1 minus some number x1 minus another number, etc. So imagine it's just the product of some linear factors. Maybe not s. Okay. And F2 is similar. Okay, etc. Okay, I'll draw a picture in dimension 2. So what is this? The zero set of F1 in this if it's in dimension 2, this is just a union of vertical lines. F2, it's a union of horizontal lines. And how many exactly the degrees of those polynomials? So the in this case, of course, it's clear that instead of the intersection points, we'll have exactly the product of the degrees. This is just, it's agreed. And it's also clear that this is going to happen even if you actually imagine that this lives not inside the plane, but inside a projective plane, right? At those points of infinity, this vertical lines don't intersect horizontal lines even at infinity. Okay, so this is all good. So that's thinking projectively, it's kind of okay. And now, so this is some equation of degree d1. This is an equation of d2. Now imagine you perturb this equation a little bit. Okay, I'm thinking about your real numbers. Okay, of course, now. Then, as you perturb the equation, now this line start to wobble in some way, depending on perturbation, they become no longer straight lines. But as you wobble, the intersection points move continuously. Because you wobble things continuously. So number of intersection points is not going to change if you wobble slightly. What might happen, you stimulate wobble the second set of lines, and since the projective plane is compact, you should not be able for things to disappear. Okay, this is the intuition why you should expect something like this to be held. Of course, this is no proof by any stretch of imagination, but this should tell you basically why you should expect. So in fact, the Zu's theorem, if you have studied it correctly, the number of intersection points is not just at most, it's actually equal to the product. But then you need to count points at infinity. Then you need to worry about that sometimes points be having multiplicity because like you can once these things wobble, some points may coalesce. Okay, so you need to define multiplicity, and I definitely do not want to do this in these lectures. Okay. So, but this is the form which is very useful already, and we're going to use it in this form. Okay, so let's take a break. Donuts and coffee and whatever else people need to feel ready, and then we'll do a construction for which I promised. Okay. All right. Hopefully everybody had some sugar and coffee. Let's continue. So the plan is to make a construction for a KST-free graphs where t is much larger than s and exponent is correct. So basically, this one. All right, the definition of variety. So let's continue here. Okay. So let's start. Need to start a tiny bit easier problem. There is a variation of Turan problem which is called Zerankevich. So problem actually. So it's goes for as far as we are going to be concerned. What it will look like is this: we have a say n versus n left, so bipartite graph with n plus n vertices, and we forbid the KST, but with very specific way. S vertex will be on the left and T on the right. So we forbid S T. Again, this is on the left and this is on the right. Okay, so we're not going to forbid S vertices here and T vertices here. So it's and this is tiny bit easier. And again, we will, so let's start with that. Okay. So the goal is to construct. So the goal construct a graph with a correct number of edges and no KST with S on the left. All right. Promise. This will be a random algebraic construction. We're going to define edges by some polynomials. Okay, so let's do that. And first, first, let me tell you what construction will look like, and then we'll give me some limits to analyze. So construction will look as follows. On the right, we will have an S-dimensional space, so over F cubed, and on the left, we will have a bunch of polynomials. So for each point on the left, so points, let's go to P. We're going to pick a polynomial f sub v, and we're going to define edges using that polynomial. Okay, so here we have a technical point which we can resolve in two different ways. So I will what I will do it slightly more complicated, but nicer looking way to resolve the technical point. So I will define my graph in a nicer way. So polynomial f of v, and I'm going to make my edges to be exactly what you expect. So this is v, this is a point, and the edge, if polynomial is 0 at that point. So much like what we did before, we had the wrote a polynomial, and the incidence between a point and point were given by vanishing of that point. We're doing exactly the same thing. The difference we're doing is that polynomial varies from point to point on the left. Okay, so I should probably say this polynomial is in polynomial in S variables. So this is applied to the. Okay, so that's what we're going to do. And we're going to choose these polynomials at random. We're going to pick each polynomial independently all right. So and at the very end we need to do a little more, but okay, for now this is enough. I haven't told you degree. Okay, good point. So at random among all polynomials, certain degree d. We will choose this degree shortly as but to basically kind of announce it, it will be approximately s to the so give me a second without looking at the notes, about s squared. It will be about s squared. So again, we will see what comes out.
So all the coefficients are in FQ, not in the closure or anything.
Yes, yeah. So this is yes. So this is yes. The
I guess that.
polynomials is coefficients of FQ. And this is why we actually can speak about choosing a random polynomial, because such a polynomial has, okay, some number of coefficients. The d plus s choose as coefficients, and each of these coefficients has few possible values, and we just pick off each of these coefficients uniformly at random, and we get uniformly random.
You want to degree exactly the you are at mostly.
Yes, among all polynomials of degree at most. Thank you, thank you. Yes, I don't want to, yeah. All right, let's do it. So a first lemma, we will need, so this is visual, let's keep it here. So first lemma we will need is well, that's this if I have bunch of points, distinct points in F bar S, then oh, and I need more conditions, sorry. And my field is big enough, and my degree is big enough. Maybe there's minus one, but it's this. Let me say this correct. Okay, this is not going to be important. Degree is big enough. Field is big enough. Then there is a direction. So that if you look in that direction, all these points have different are different projections. So there exists a linear function the xs say C S. So let me just this such that all these projections onto these linear functions TPS
It looks like X to the S.
It's because indeed it was X to the S, it should have been X somewhere. Yes, the question.
There's no condition.
It doesn't matter. It's a proof of it. Don't worry. Everything is fine. Okay. So we found.
Is there a relationship between M and S?
No, this is for NAS. So this is OP. My typo. My apologies.
Does capital D appear?
This is, oh, sorry, this was wrong. You're right. No, sorry, this is not them. No, sorry. This is all. Sorry, I was thinking the condition for next lemma, which where that thing would happen because but for now we don't need it. Sorry.
So
Of course not. Thank you.
The constants here are in FQ, not in FQ bar.
Yes. So this is CI. Right. Otherwise, we would not need any conditions on the side of it. Yes.
C1 always.
Yeah. Basically, it will be just that time easier to say what the next thing I'm going to say for this. This is basically why, but you know, it's not. If put C1, it's also going to be.
So from C to CS, there can be zero coefficients. There can,
This so CS can be some of them will be zero, of course. I mean, it might. I mean, maybe these points really have the different x1 coordinates.
Mhm.
I mean, in which case we can just take the C's to be zero. Okay. For the proof, let's consider some pair of points. So, consider some PI and PJ. So the set CS such that images are the same. All right, so I'm looking at set of bad choices of the coefficients. Okay. Bad in the sense that the ith point and jth point are going to map to the same thing. Now, this thing is a linear equation in C's, and because the points are distinct, not every tuple of C's is a solution. So it's an affine subspace of it's an affine subspace and it's of dimension strictly less than x. So this bad set, the J, Bij has no more than q to the s minus 1 points. So finds space of dimension strictly less than s, so the number of points is no more. So now what are all the bad sets? So if I look at the union of all of this, well, there are M choose 2 pairs IJ, each of them gives me a set of size at most this. And so since M choose 2 is less than Q, this is strictly less than Q to the S, and so there exists some choice which is not in that union. And that's all we really want.
I think there is, but there's Q S minus 1 choices for C2 to CS. So is it really Q? I mean, is it really Q to the S minus 1 there, or Q to the S minus?
Minus 2, yes.
And then-
Thank you. So it's codimension 1. That's what I should have said. Yes, but the dimension here is so it's S minus 2. Thank you. So this is S minus 2, and the total of them is S minus 1.
Yeah.
And then that's this correct is written. Thank you very much. All right. So this is dilemma. Okay. The point of this lemma is that it allows us to change a coordinate system so that given set of m points have distinct force coordinates. So this is basically a little bit. So this is what we're going to use in the second lemma. So lemma 2. This was lemma 1. The so again, suppose we have quite a few distinct points. That's we have the condition, and now the condition which I wanted to add last time, but I think it was here. The degree is large enough. I think -1 is all we need. But it's not going to matter. Degree is large enough. Yes, that's all we need. And F is a uniformly randomly chosen polynomial. Among all polynomials of degree at most d, then the probability that this polynomial vanishes at all of those points is rather small. So F vanishes at P1, vanishes at P2, F P and 0. This is at most 1 over Q to the M. Okay. Let me just maybe say a couple of words about the statement of this lamp. So first of all, this right-hand side is natural because if I imagine I have some point, just think about a single point, and suppose this point lives is in FQ. So basically all coordinates in Archial field, not in this bigger thing, but just in FQ. And I'm choosing a random polynomial, and I'm asking, is this polynomial, does this polynomial vanish at this point, or does it not? Well, then the probability would be equal to exactly 1 over Q, because, okay, we're going to choose coefficients of this polynomial 1 by 1, but we're going to choose the constant coefficient last. Okay. And then probability that we're going to choose constant coefficient just right to make the whole sum of everything 0 is just, well, there's only one choice, and they're out of Q, so it's going to be 1 over Q. And this, so now if you have if you have the M points, you would hope that there is an independence between values of polynomial at the different points, in which case it ought to be 1 over Q to the M. And there is indeed independence, assuming degree of polynomial is large enough. This is what we're going to essentially show, right, in the proof. And this is tiny bit more general lemma, if you might, or some sense it's more general. I'm now allowing the points to have coordinates not just in FQ, but in the bigger field. And this inequality says, well, it's only going to be harder to be 0 if you actually use logic. Okay, so it's smaller. That's really the what this is. Okay, so let's then start on that lemma. So the okay. All right.
Points.
Okay, so by first lemma, there is some we can find linear T linear T such that this point is distinct. And the key observation is that when choosing, I can change my back coordinate system. So hence there is an what is it? An invertible transformation L I cheat slightly. Let me cheat from S so from F S to itself. So in other words, such that LP1, LPM have distinct force coordinates. Okay. So in other words, what we're going to do is to define this linear transformation. We're just going to use T for the force coordinate and basically complete it to a basis. And this actually where it helps, we can just basically keep since our theory found actually has x1 to be coefficient 1, we can basically just take L to be just x2 for x. This is basically what I'm using tiny bit so that I can take my L of x to be T of x and then x2 x3. Again, here I'm using the coefficient of x1 and t is okay. This is minor. Okay, and the point is if whether I can picking picking a random f is same as picking a random f composed with L inverse, right? So in other words, if I pick a random polynomial and then apply a fixed invertible change of coordinates, it's still a uniformly random polynomial. So in other words, I can actually just take my points, apply this linear transformation, and just work with those transform points, and this because I can just think of applying this polynomial which undoes this linear transformation. Okay, so this means this is here. No, I think I need to go move that. So without loss of generality, the force coordinates of these points are this. All right, now we're going to do the argument, which is much like what I spoke verbally about a single point. I'm going to think of my polynomial as a sum of two terms. We shall call them G and H. Where G consists of all the constant term, linear term in X, quadratic term in X. Next one, up to the X m minus up to the coefficients. I'm sorry. X. Okay. So that was these are the terms in powers of x1 up to m minus 1, and the h is the rest of the polynomial. So I mean, so most of the terms are in h because f is a huge polynomial. It's and h on the rest of the terms. In particular, h contains all the terms which involve variables other than x1, x2, x3, and so on. Okay. Then I'm going to think of first picking h at random. Pick h first. And then we're going to ask, can we pick G to, okay. So once H is fixed, and the F of Pi equals 0, it's the same thing as the G of Pi is equal to the negative HPI. Now, H we already have chosen, so on the right-hand side, this is just some number. Okay, by number, I mean this number is an FQ bar, because P points Pi is of coordinates in FQ bar, even though the coefficients of H are in FQ, I mean, I'm still going to get something in this bigger field, potentially. Okay, so now I'm asking, are the values of G at this point going to be equal to something? But there's going to be but you know, if I have a polynomial of degree n minus 1, I want to know want to have values, particular values at m points. There's only one choice of these coefficients of this polynomial to make it so. There's only one such polynomial. And so, therefore, there exists at most one such choice. So, for each H, there is at most one F, at most one G that satisfies. The reason I said most one rather than exactly one, because it might happen that the coefficients of G are going to be in FQ bar, not in FQ, right? Because we're choosing a G from coefficients FQ, but if once you solve that, it might happen that the coefficients are actually in FQ bar, but there's no more than one solution, because even in FQ bar, there's only one solution. Well, that's exactly what you said. Probability is 1 over Q to the M.
It includes that it points that PI to be in FQS initially, then this equals that PI.
That's equality. Very good comment, yes. Yes, if points are in coefficients in FQ, then it's actually equal. I mean, the way we can say it is the values of the polynomials at points are actually independent. Maybe let me actually remark it, because this is actually something we will actually use later. remarkable. So if E1 are in FQ less and distinct, and the degree is at least n-1, and we have the conditions on the field being large enough. I mean, the condition on the field being large enough is easy to satisfy because in all our constructions we will take it to infinity. We want bigger constructions. So that's actually essentially non-condition. It's not important to hold. And then the F D1 and D2 and P to the M are independent random variables. So again, each of them is a random variable, right? It takes if F is a random polynomial, it's a random value, take in F cube, and we have M of them, and this proof shows that this is actually independent random. All right.
So basically this G has to be 0, right? Because the degree is m-1, but you have m distinct. 0 is.
Not sure.
I mean, so G has m distinct roots. If you want-
Yeah, G is a random polynomial, right? So okay, so we're choosing it's random polynomial F, and we're choosing in 2 stages. First, we choose all coefficients which are in H, and then we choose G. And we are not looking at the roots of G, right? We are looking at the values of G at this particular point.
So I think that is, the at most one comes from the application of the under one since the term.
Well, okay, you're asking how do you prove that there exists exactly one solution to this system? This is one way to think about it, right? You know, okay, depending what you want to assume, yes. So one more German. This is one way. Another way is saying that G of P is equal to A means that let's think like this. Yeah, I wonder more the German probably. If you actually want to prove it, probably this is the way to prove it. I'm thinking, yes, I don't think of maybe on the spot. So I can't think of a simple proof on the spot, right? So yes, because what we're doing, we're looking at the equations of the form, right? CI, not called CJ, sorry. CJ EI1 to the power J. This is equal to those constant as well as CI. That's the right hand side. Oh, not CI. Yeah, so this is one Drummond matrix times the coefficient is equal to 1, and you work on the yes. I feel it should be easier to prove, but yes. Not the start. Okay. All right. I was hoping to finish today, but I mean we are out of time. So okay, but it's a good place to cut off. We will finish proof tomorrow. So we have a lemma about browsing the independent, and we're just going to apply to our construction, and there's going to be just stroke calculation all done, and we can do this and look at the various variations. Okay, so let's stop at this point.